summarize that, then, looks something like this. And the energy required to change the voltage, if you will, or the energy stored when you increase the voltage, related to 1/2 the capacitance times the final voltage, minus 1/2 the capacitance times whatever the voltage was prior to raising it, or even lowering it. So the energy that comes and goes is directly related to the voltage on the constant capacitance. So you're not changing two things. Again, it's kind of like having Q divided out. When in doubt, divide Q out. We typically treat things only in terms of V because, as I stated many times, charge is hard to measure. It's easy to calculate if you know V. But charge is hard to measure. So if you wanted to charge a cell membrane, from 0 to 8 millivolts. And we'll use our previous example. Then the stored energy would be equal to 1/2 the capacitance of the cell times the square of the membrane potential, which is this number here, or 1/2. We say it was like 6.67 10 to the negative 14, a ridiculously small number. Times 0.08 volts squared. That is 25, 30 times 10 to the 14th, 15th, 16th, 17th, negative 17th or so, negative 16th, 15th. Not a lot of energy. Oh no, 64. A little bit.
2.14 times 10 to the negative 16.
16, about that order of magnitude. 20 times 10 to the negative 17. That's 2 point something times 10 to the negative 16. Okay. 2.1, 2.0. Okay, so bottom line, how much energy does an electron have in just an atom? Roughly 10 to the negative 18th joules. We calculated that one a couple of times. Didn't necessarily like the calculation on the exam, but we calculated it a few times. So 10 to the negative 18th joules. The amount of energy, that's just the base energy of an electron sitting on an atom, particular atom we've been looking at. The amount of energy and work associated with charging a cell membrane is only about 100 times the base energy of a hydrogen electron, or an electron or a hydrogen atom. It's tiny. It doesn't take much energy. We use this membrane voltage for signaling and for various cellular mechanisms, but there's very little energy. It's a signal transmission a lot more than it is a physical energy process. The energetics are not involved in keeping this thing at a certain voltage, but rather whatever other cellular processes that are happening. Okay, get the hell out of here. I had a whole bunch more stuff to talk about, but I know I'm not going to keep your attention anymore. This is a lot of stuff. To me, it's like, oh, it's just a little this, a little that, but I know.